Who is not here? Okay, so we'll go over the power exploration, and then we're moving on to the next set of notes, which will allow us to introduce some new terms, new characterizations, ways for us to describe different parts of the graph of a polynomial function. We'll really dive deeply into polynomial functions and graphing polynomial functions. So I will send you off with that information. For the long weekend, you have plenty of math practice problems as well in the packet for you to be working on. Josh, did you have a question?
Yeah.
Go ahead. Okay. No, that's all I was going to say.
How do you apply, like, knowing whether a function is even or odd and really well?
Like, why is it important?
Yeah.
Okay, depending on what the graph represents. So sometimes you can have mathematical models, right, that are modeled by functions. And if you look at the graph, it'll tell you important things about the property of the function. What we will see today, for example, where you think, can I answer the question after we talk about long-term behavior today in the tails? Okay, remind me and I'll answer that question for you. Really, if you look as time goes to positive infinity or negative infinity, when you look at that behavior, that tells you something about the nature of the model. As the model gets more and more complicated, when we're working in higher dimensions, let's say, it gives you insight into predictions and conclusions that you can make. Because if you can say algebraically it's symmetric, then you know what's going to happen in the future based on what's happened in the past. Does that help you?
Yeah.
So if today is time equals 0 and I know what happened in the past to the left of the y-axis, then I may have a better idea of what's going to happen. That's kind of vague answer until we talk a little bit more about the terms that we're going to use today. Does that help a little bit? Okay. All right. Welcome. What I wanted you to do with the power function exploration is I wanted you to populate the tables, and then you were asked some very interesting questions about some things that the tables shared, and then perhaps looking at how the power impacts the graph. So what I wanted you to do is I wanted you to populate the tables, but then I wanted you to like investigate, you know, certain things that were happening, certain things that they all shared, certain things that certain powers shared, right? This is what I wanted you to kind of notice. Then what I also wanted you to do is I wanted you to do a quick little sketch to the right so that you can see, based on the power, what the shape looks like. And so this is, you know, kind of giving you an idea for even powered parent polynomial functions versus odd powered polynomial functions. Parent functions, right? So this is kind of what I was hoping for you to be able to recognize before we started answering the questions when you first looked at the tables and their quick little sketches. So let's go a little bit more in detail. And again, this continues with the odd and with the even and with the points that they share, right? And ones that even powered parent polynomial functions had and odd parent polynomial functions. So if you used your graphs, I wanted you to describe what you notice about how increasing the exponent affects the parent functions. So for even powered parent polynomial functions, I wanted you to notice that we were still, you know, kind of just opening, let's say, as we read the graph left to right, but as we increase, it's either getting fatter, you know, wider, or not. For odd, hopefully you noticed that we were passing through the first and the third quadrant at all times, right, for the parents, but the steepness, how fast we approach infinity in the y, depends on your power of x, right? As we increase the power of x, how quickly do we go to infinity? Y goes to infinity faster and faster every time, whether it's positive infinity and negative infinity or positive and positive infinity. So that's what I was hoping you noticed there. What do the graphs of the odd-powered exponents have in common? Again, if they're odd, we notice that they pass through the first and third quadrant only in the origin, right? They're not symmetric with respect, even though they kind of look like it, right? So things were a little bit different going on. With respect to the even-powered function, hopefully you notice that they pass through the first and second quadrant only. It's not true for all functions when we vertically translate parent functions, right? If we shift the parent functions up and down, we may drop down below the x-axis, and therefore we're passing through other quadrants, but the parents pass through first and second quadrants. Now, the next thing I wanted you to look at is the fixed points. Are there any fixed points among all or any of the functions? Well, they all pass through 0, 0, and 1, 1. All of them pass through 0, 0, 1, 1. Additional fixed points with respect to the evens is they pass through negative 1, 1. What quadrant is that in? Negative 1, 1. Quadrant negative 1, 1. Quadrant 2, right? And then for odd-powered functions that pass through negative 1, 1, we said that they pass through the third and first quadrant, right? So what's happening as we increase the powers, right? We start like this with our, well, we start like this for our linear, y equal x, x squared, x cubed, x to the fourth, x to the fifth. See, it passes through 1, 1 in the origin all times, right? Does that make sense? Isn't that kind of cool? That's cool. That's cool. I like it. It's fun. Okay, that's what I wanted you to get from this. Now, you should also be able to notice which are even, which are odd, right? Symmetry about the y-axis or symmetry about the origin, the x and the y-axis. For the parents, they directly correlate to the power of the function of x. Not true if we are looking at transformed functions. So let's go ahead and go back to our notes. And today we are going to talk about some more properties about polynomial functions and then look at how to graph polynomial functions. So let's first look at the definition of a polynomial function. Now, when you first see this, you may go, oh my gosh, oh my gosh, oh my gosh, this is very stressful. But once you see it and you understand the components of the definition, it's not hard at all. Okay, so I have a function. So we're talking about the definition of a polynomial function in one variable. So I'm going to call it p of x, y equals p of x. It's a polynomial function, a single variable x, if and only if it can be expressed in this form. So y is p of x, so p of x equals this. So what does that mean? Well, I have x to different powers. Notice that my powers are numerically descending powers of x. So I'm starting with n, x to the n, and minus 1 smaller degree of x, smaller power of x, all the way down to x squared, x to the first, x to the 0. So that's all that notation is showing you, that I have decreasing powers of x. Now, for every power of x that I have in this general form, whatever the degree is, they each have a coefficient. So these are just denoting the fact that you have coefficients of each of these powers of x. The subscript of that coefficient value a, let's call it, corresponds to the power of x. So if I ask you, what is the coefficient to x squared? It would be this number. That little subscript of 2 is just saying I'm the coefficient for when the power of x is 2. I'm the coefficient when the power of x is 1. I'm the coefficient when the power of x is 0. And when the power of x of 0 is 0, then it's just 1, right? So this is technically 1 times a sub 0. So it's just a sub 0. It's just the constant. Does that make sense? Does this notation make sense? This is just defining that each of these little coefficients are elements of the reals. They're just real coefficients. The leading coefficient, a sub n, cannot be 0 or then it's one less degree of the polynomial. And then these n's that I am using are just whole numbers. N cubed, n to the 4th, n to the 5th, just whole numbers all the way down to n equal 0. So n is called the degree of the polynomial. So if I give you a polynomial, the highest power of x is the degree of the polynomial, if the polynomial is in a single variable. This a sub n, the coefficient of the highest degree of x, is known as the leading coefficient. And again, a to the 0 subscript is just your coefficient of x to the 0, which is just your constant. So my recommendation to you is to always put any polynomial I give you in standard form. What is standard form? Exponentially decreasing order. It's in your best interest to put it in that form. So what are some examples of polynomials? Well, let's look at some examples and you tell me, are they polynomials based on this definition? So if I give you p of x, and I give you this, does this satisfy the definition? Yes, it does, right? It's a single variable. My exponents of x are whole numbers. My coefficients of x are real numbers. So if you remember back to when we first talked about polynomials, we classified polynomials based on their degree and the number of terms. So you should be able to state the degree and the number of terms, but then in turn, classify the polynomial. So what is the degree of this polynomial? It is 5, right? It's the highest exponent of x. How many terms does it have? It has 3 terms, 1, 2, 3. Remember, addition and subtraction only affects the number of terms, not multiplication or division. So how would I classify this polynomial based on the degree and the number of terms? Do we remember? Or quintic, right? But it is a 5th degree trinomial. So you should be able to classify.
Will this be on the best classified?
Well, maybe.
Will you take the degree trinomial or do you want the...
For 5, we know those names. Anything above 5, just stating the number of terms is fine. But we know cubic, quartic, and quintic. Now, what is 2? What is it? What do we call a polynomial that's degree 2? A quadratic.
I thought that was 4.
That's quartic.
Why is it quad?
Oh my goodness gracious. Okay. So,
That makes no sense. Quad is 4.
yeah. Okay. So let's go ahead and talk about what happens if I give you the polynomial in factored form. So what if I give you this? What if I gave you that and asked you to write it in standard form? What would you do?
What would I foil first?
I would FOIL this and then distribute that to each of the terms after I FOILed. Okay, so when I did that, to be able to answer the question easily, you might want to put it in standard form first, right? It is then that you can easily identify the degree and the number of terms. Don't just look at this and go, oh, I see a power of 4, it must be, right? This is multiplication going on. So what is the degree of this? 6, right? So this would be a 6-degree trinomial, right? So be careful, don't fall for it. If I give it to you in factored form, put it in standard form.
Did you just do all that in your head?
Yes and no. All right, let's go ahead and look at this. What if I give you these? Let's talk about why they would not be polynomials. Okay, what if I give you f of x equals, and I don't have to give you p of x for it to be a polynomial. Why would this not be a polynomial? What part of the definition is not satisfied? That's right. If I rewrote this without the radical expression, what would be the power of x for this term? No.
Oh, no, 3.
The power of x for this term, 1/2, right? This is a radical expression. We should be able to rewrite radical expressions with rational exponents.
But should we not be, shouldn't we?
What are you saying?
I thought you said that, you shouldn't have a rational exponent.
It has to be a whole number. So the fact that this is a rational exponent, a fractional exponent, so therefore it is not a polynomial.
And wouldn't the 2 have to come in front?
Well, if I were trying to write it in standard form, but yes, but I already know that this is not a polynomial equation because of the rational exponent. Okay, what about this one? Why not? Okay, so how would I bring this to the numerator? What would the exponent be if I wanted the x? X to the what? How do I move that?
Oh, you have to multiply by the reciprocal.
-2, thank you. Mia, you want to explain why? No, don't say that word. We negate the exponent. Yeah, we negate the exponent. To bring that to the numerator, remember you changed the sign of the exponent when you cross the dividing line. You need to be able to do that.
Oh,
And
so
so the fact that we have a negative exponent means it's not a polynomial equation. Okay, so I'm going to give you equations. You need to be able to determine whether or not they're polynomial equations based on the definition. Now, let's say you are given polynomial functions. There's a new term that we need to be able to use and recognize in a function. We call a polynomial function smooth if the graph of the function has only, let's say, rounded curves with no sharp corners. So examples of smooth. Can anybody tell me a graph that we may know and love that
x squared.
y equals x squared? Yeah, that's smooth. Anything else? Yeah, that's smooth. Can we think of a function that we've seen that is not smooth?
Oh, y equals absolute value.
Yeah. Beautiful. That's a sharp corner. Okay. Some other examples might be, you know, piecewise functions, right? Those that has sharp, right? So these are not smooth. These are smooth.
Wait, is y equals x smooth? Because it doesn't smooth, right?
No short corners, yeah, goes on forever.
Oh,
Okay, we call a polynomial function continuous. That's a math term. If the graph of the function has no breaks. So it can be drawn without lifting your pencil. So again, continuous, we could still use y equals x squared. That still works. I mean, I lifted my pencil, but I could draw it without lifting my pencil, right? Or I could have this. That's continuous. That's a hideous function, though, so let me just leave it. Right? Things that are not continuous, piecewise functions. In some instances, I could have this, and then I could have to lift my pencil and do this, right? If I have to lift my pencil and put it back down somewhere else, there's a break. It's not continuous. Yes, Josh.
What about y is greater than x?
Y is greater than x? You're shading a half plane for that.
I know, but what if you...
So we're just talking about boundaries. We're just talking about curves. We're not talking about inequalities. We're talking about equalities right now. Right?
So if not, like the not smooth piecewise function, that's still continuous, though, right?
Yes, 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 yes. Which brings me to something interesting. You know, you may want to think about the relationship. Can you be continuous and not smooth? Can you be smooth and not continuous, et cetera, et cetera? So think about that. Blaine, did you have a question?
You have a price function and two lines that intersect each other.
No, they can't intersect each other because then it wouldn't be a function, for starters. I like it. I like the thinking, though. This is good. This is good. Very good. All right. There's something else that we can use to describe graphs, in addition to being smooth or continuous or not smooth or not continuous. And that requires our looking at what's known as the end behavior, also known as the tails of the graph. The tails, the end behavior. So you will have to look at graphs and you will have to describe the end behavior, what is happening in the tails. So if we look at the leading term, the coefficient, the leading term, in particular, the coefficient, well, and the leading term, that is going to tell us about the end behavior, the tails. Okay? So again, I like to put everything in standard form and then focus my attention on that leading term, the coefficient and then the degree. So if you have a polynomial as we defined, if the sign of a sub n, the leading coefficient, if the leading coefficient is positive, greater than 0, then we know the right tail is going to go up. So it's going to look like that, the right tail. So the coefficient, the sign of the coefficient tells us the right tail. The sign of the coefficient tells us the right tail. If the leading coefficient is a negative number, then I know that the right tail goes down. Again, the sign of the leading coefficient tells us the right tail. Now, going back to that leading term, if the degree of n, the leading term, is even, that is going to tell us what the left tail does, okay? If n is even, both tails go in the same direction. In other words, have same end behavior. What does that mean? That means they either both go up or they both go down. So I look to my leading term. If it's positive, the leading coefficient, I know the right tail goes up. If the degree is even, the left tail also goes up. If the degree is odd, but the leading term is positive, the right tail goes up, but the left tail goes down. So if the degree of the leading term is odd, the tails go in opposite direction. Different in behavior. So in other words, I look and I see that the right tail goes up, so the left tail will go down. Or if the right tail goes down, the left tail will go up. So if I give you examples, you should be able to tell me immediately what the graph is going to look like. Okay? So for example, if I give you y equals 2x to the fourth minus 3x cubed, it doesn't matter what the rest of this is, what does the right tail do? Look to the leading coefficient. I see the leading coefficient is positive, so what do I know? The right tail goes up. Okay, and then I look to the degree, and I see the degree is even, so what do I know? Left tail also goes up. Right?
So if the degree of a polynomial is even, or not a whole number, then it's automatically even.
If it's a whole number, it's even? No, even means it's divisible by 2.
So if it's a whole number that's divisible by 2, then it's.
So like if it was 3, it would be odd.
Then what's the point I think we learned?
Even and odd function has to do with symmetry, right? Symmetry. Is it symmetric about the y-axis or is it symmetric about the origin? That's not directly correlated to the degree of the polynomial unless we're looking at parent polynomial functions, right?
It was like determining whether it was even or odd.
Right. Not the degree of the polynomial, whether the graph is symmetric about the y-axis or symmetric about the origin. That's what even and odd told you. That had nothing. That wasn't, you know, that wasn't exactly evident based on the degree of the polynomial, unless it was a parent function. But if you think back to the parent function, right? Power of 2, power of 3, power of 4, power of 5. Remember the tails, the same, opposite, the same, opposite, right? That's not the same as symmetry. All right. How do we find the zeros of a polynomial function? Well, we've looked at polynomial expressions. We've factored polynomial expressions. So you should be able to find the zeros or roots of a polynomial by looking at the x values that make y go to 0. They give us the x values of the x-intercepts. And if they are real values, they tell you where the graph crosses the x-axis. So if you think back to when we were talking about quadratic functions, if it passed through the x-axis, then it had 2 unique real values, real solutions, 2 x-intercepts. We knew that because the discriminant was positive. If it touched it and bounced up but didn't pass through, we had one unique real solution. It was a repeated root for a quadratic equation, right? The discriminant was 0. And then if it never crossed the x-axis, it had complex solutions, and the discriminant was negative. So we're putting all of this together, okay? So an nth degree polynomial function has how many roots? N. However, some roots may not be distinct. In other words, they may be repeated roots or multiple roots. And you would have to describe the multiplicity of the roots. But let's first take a look at this example. Is it a polynomial function? By definition.
Yes.
Yes. What is the degree of the polynomial? Is it in standard form? How many terms does it have? 2 terms. How many roots should it have? 4, based on the degree of the polynomial, right? What does the right tail do? How do we know it goes down? Right, the right tail goes down because this is a negative number. How would I classify this polynomial? Quartic, 4 term, binomial, fourth degree binomial, 2 term, 4th degree. What is the leading coefficient? What does the left tail do? Because the right tail went down and it's an even degree polynomial. Now, could we actually find those roots? Oh, come on, let's do it. Yes, we could. I just set it equal to 0, right? And what would I do to the left-hand side? What would you want to do? I'm going to, yeah, negative 2x squared. What would that leave me inside the parentheses? Do I stop there?
No.
Difference of 2 squares. 0 product property says I can set each of those equal to 0, so I get 1 root, 2 roots, 3 roots, 3 solutions. Now, this is the solution to a linear equation. So it's a single root. This is the solution to a linear equation. It's a single root. This is the solution to a quadratic equation, right? If I were to set each of these equal to 0, are you with me? This would be negative 2x squared equals 0, x plus 1 equals 0, x minus 1 equals 0. So this is a single unique root, each of these. This would be a double root. And the multiplicity would, well, we know it's 2. Multiplicity 2. It's a repeated root, right?
How would it touch, like, multiple times?
How would it touch? Well, we're not quite there yet. We're going to talk about graphing in a minute. So let's talk about identifying zeros and their multiplicities. Identifying zeros and their multiplicities. So we said if a root has even multiplicity, the graph touches, and this is based on what we know with quadratic equations. If the root has even multiplicity, the graph touches the x-axis and changes direction. For example, y equals x squared, right? Touches, changes direction. Single valued root with multiplicity 2. If a root has odd multiplicity, the graph crosses the x-axis. So for example, y equal x. right? Single unique root. Or y equal x cubed, right? So let's go back and talk about this a little bit more. I know where my roots are, so I know my intercepts, don't I? I have an intercept here. I have an intercept here. I have an intercept here. Are you with me? We said the right tail did what? The right tail went down, didn't it? What did the left tail do? It also went down. We know that this is a single root, so I'm crossing. I know this is a single root, so I'm crossing. Now, I would have to find more information to see how far up it goes. I could substitute x in equal and a half, x equal negative half. I'm not concerned about that right now. What I'm concerned about is I know that it does this. Do you see why? Since these are unique single multiplicity roots, multiplicity 1 here, single unique roots, it crosses. It touches and changes direction because this is a double root at x equals 0. So I can do a quick sketch of a graph, right? It's not as 100% precise because I don't really know how far. It could technically do this, right? I'd have to get more information to know that. But I'm not concerned about that. I want to know you know what the tails are, you found the roots, and you know what's happening on the x-axis at the roots. Yes? Okay. There's a theorem, intermediate value theorem for polynomials, intermediate value theorem. If P is a polynomial function, and if P of A, so P evaluated at some input A, and P evaluated at another input B, have opposite signs, then there is at least one value, we call it C, in between those two values, A and B, in that closed interval, such that the polynomial evaluated at that value in the interval has to be 0. So what does that mean? Well, let's take a look at a graph and see if we can understand what this is telling me. I have a polynomial. I have an interval, say A. So the polynomial evaluated at that interval is P of A, right? This is A, this is P of A. I have another point, let's say B. So this is the polynomial evaluated at B, the output, right? So far, so good? So I have my interval A to B. You see that interval? It's saying in that interval, there exists a point, which we will call C, in this interval, such that the polynomial evaluated at that value, C, equals 0. So it's just saying that if I have 2 points on the graph, one has a negative output, one has a positive output, there must be a root in between. That's all the intermediate value theorem tells you. Does that theorem make sense? Okay. We have to be able to read theorems, write, draw little graphs. So here I've given you a polynomial, and I said, I want you to look in this interval. There are my endpoints. And I want you to tell me if there exists a root in that interval. Well, how am I going to do that? I'm just going to take the polynomial and I'm going to evaluate it at one endpoint. Then I'm going to take the polynomial and evaluate it at the other endpoint. And if those have opposite signs, then there exists a root. So if I take that first value in the interval and I evaluate it, what am I going to get? -1. So that is less than 0, right? That's below the x-axis. Then I'm going to do the same thing for the other endpoint of the interval. And what is that going to give me?
The top ones are just one.
And the bottom one.
No, see if I listen to you. So if I evaluate it at -1, I get 3. I'm going to do it. That's 7. Right? So that's positive. Then I'm going to do this one. And what do I get? Since these are of opposite sign, then by the intermediate value theorem, there exists at least one x value in the interval -1 to 1 such that p evaluated at that value equals 0. And I should technically write x value c in that interval. So do you see how I can say that? Okay, let's look at an example. We want to show that this polynomial has a real 0 between 2 and 3. So do we know my closed interval? What's my interval? Closed 2, 3. Oops, closed. I want to see if this polynomial has a real 0 in that interval. So again, evaluate the polynomial at each endpoint of the interval. The function evaluated at x = 2 is what? -1. So that implies that this point is 2, -1. So that's below the x-axis. And then this one is what?
-2.
No.
16.
Yes. I'm not going to take y'all's word for it immediately now. Do it in my head. Right? So I'm at this point, which is above. So since f of 2 is less than 0 and f of 3 is greater than 0, then there exists at least one x value, c, in the interval such that f evaluated at c is 0. Oh. Okay.
But isn't this theorem just kind of common sense?
Yeah, it is. It is. It is. But that's how you algebraically show it. Yes, absolutely. You are correct. Now, a polynomial function of degree n has how many roots? N roots. How many turning points does it have? It has a maximum. It's not telling you the exact number, but it's telling you at most it has n minus 1 turning points. 1 turning point less than the degree of the polynomial. I don't know how many it has, but I know it has at most 1 less than the degree. So let's look at some examples and possible graphs. If n equals 1, what type of function am I looking at? If n equals 1, if the degree of the polynomial is 1, what is it? It's linear. Right? If n equals 1, the degree is 1, it's linear. So what is the maximum number of turning points it can have? 0. So let's think of the only possible graph I can have. Well, it's just a line, right? So no turns, 0 turns. That doesn't look like the word turns. Okay, what if n is 2? It is quadratic, right? Let's go, let's do it. Okay, so how many turning points maximum can it have? Well, and we know it's a parabola, right? Can open, right? Where's that turning point? Right there. Okay, what if it's degree 3? What are we looking at? It is cubic, yeah. At most 2 turns, at most, but it can have less.
So it can be a parabola?
No, it cannot.
How can it have less?
I can be like this, y equal x cubed. If it's cubic, I know my tails are going in different directions, right? My tails have to go different directions if I'm a cubic polynomial. So the only way that can happen is this or this. So where's the turning point? Here. Where's the turning point? Here and here. So this implies that I can have either 0 or 2 turns.
Oh.
What if it's degree 4? It's quartic. Maximum number of turning points is?
Wait, how
Or
was
it
that
would be
0
one,
turns?
one or one.
You mean 1 or 2, right?
No. This is 0 turns.
It's still in the same direction.
Still going in the same direction. This is 2 turns. Sorry, I shouldn't have done that. Do you see why that's 0 or 2?
Yes.
Okay. 4th degree, maximum number of turns. 1 less than the degree, 3. Are the tails going in the same direction or opposite direction? Same direction. If you remember your parents' functions, right? It can be that. It can be that. So how many turns? 1, 1, 2, 3. We see a pattern. And I can continue this in this fashion up to degree n minus 1. So how many turns do I have? Well, if n is odd, then I can have what? 0, 2, 4, up to n minus 1. If n is even, then I can have what? 1, 3, 5, up to n minus 1 turns. Does that make sense? Oh my goodness. So last but not least, let's do 2 examples of doing quick sketches of graphs of polynomial functions based on what we know. Okay, so here's our first polynomial function. So I like to really exploit this beautiful little function and talk about everything that I know. So what is the leading coefficient? LC, leading coefficient? 1. So since the leading coefficient is greater than 0, what do I know? Right tail goes up. And I do little information here so I can answer questions and make sure I'm graphing correctly. What is the degree? Degree is 4. So what does that mean? Since it's even, both go up. Okay. So now I need to know some information. So perhaps I want to find my roots. So I know about my roots and find my x-intercepts. So I'm going to find solutions. How? By setting y equal to 0. So then I have x to the 4th minus 5x squared plus 4 equals 0. How many roots should I have? I should have 4 roots, right? Now, what would be a nice, easy way to do this problem? Do we remember a little, huh?
Do the, like, -4, complete the square?
You really with a
You can
quartic?
legit factor.
Don't you do the U?
Thank you. Yes, yes, I'm gonna let u equal x squared.
Oh wait, you can't factor it to,
Well, you can, but if you have difficulty keeping track of your exponents, you might want to do this, which would allow you to easily factor. What are my 2 factors? U,
U -4.
yes, yes. Are those my roots?
No.
Absolutely not, because what was u? U was x squared.
X equals 2.
x equals plus or minus 2.
Mm-hmm. So I have my x-intercepts. And how many do I have?
4.
And how many solutions was I supposed to have? 4. Although they don't have to be 4 unique ones, right? We could have multiplicity higher than 1. So, yes.
For your final answer, oh wait, never mind.
Okay, so I have 4 roots. 4 solutions. 4 x-intercepts. Is there another point on the graph that I might want to know to help me graph? Y-intercept, yes. What is the y-intercept? No, it's not. What is the y-intercept in a graph again?
X equals 0.
But what graphically, what is it?
Crosses the Y.
It's the point.
0.
Oh, yes, it's 0,
Let's
4.
go. We're
Yeah.
super two.
Oh, my goodness. All right, so let's plot what we know. I know I have roots here. I also know I pass through the y-axis here. I know my right tail goes up. I know it passes through. I know it passes through, and it's going to come up here. It's going to come, that's hideous. It comes back down, and it goes back up. Now, do I really know how far down it goes? I'm kind of fudging this a little bit unless I were to find more values, right? The only thing I really know is I know this, it passes through. I know this, it passes through, and I know this. Now, my question to you is it even, odd, or neither? Do we know
Yes.
for sure?
Yep.
Can we verify it? If I think it's even, what do I need to show?
X equals F.
Well, let's show it because, we have to prove everything. Was there a property that I could have used? Yes.
Yeah, the one where it says like the degree, if it's divisible by 2, then it's even.
If I take the sum of even functions, right? Or difference, remember that property? But, we're doing it this way. X to the 4th minus 5x squared plus 4, it equals f of x. So it is even. And the maximum number of turning points? And -1 is 3. Yes. So that would be, like, in a nutshell, a big, beautiful problem on a test. Right? So I'm looking for tails. I'm looking for intercepts. Am I really looking for this? No. But I need to know it passes through. Let's do another one. Because they can get a little weird in your eyes. Let's see what we know. Leading coefficient.
3.
4.
So what do we know? What do we know from that? Right tail goes up.
Oh,
What's the degree?
4.
So what do I know?
Even.
both go up.
Do I know my x-intercepts? What are they?
1 is 0. 1 of them is 0.
Okay. How am I going to do that? Let's do it. Okay, what is the greatest common factor? Leaving me 3x minus 4. This is a cubic equation. So I have x equals 0 being a root, a repeated root, but what's the multiplicity? I should say, let me put repeated root. And then this one is going to be the solution of a linear equation. So this is a unique single root, right?
What's the last root?
Well, this is 3, this is 1, that gives me 4, I have 4. Don't I?
Wait, where's the 1?
Oh,
Which one is?
This is a single root because it's a solution to a, so what's happening at this point on the x-axis? What can you tell me about the graph there?
Passing.
Yes,
go across it.
crosses. Okay, and then I'm over here at 0. I know the right tail goes up. What's happening there? Something very special happens there with a cubic multiplicity 3 root. Doesn't just crosses, but actually has something known. Well, let's just say that. It doesn't go straight through. It kind of has a little point of inflection.
Oh, I was confused because it was x cubed, so there's 3 roots of 0.
Yeah.
Oh, that's.
So here, this here, right? Now, I might, I'm sorry? Oh, it does, but we could maybe find out what happens when x equals 1. Can't we do that? We could do that. Let's find out what happens. Let x equal 1, because that's a nice value.
It's a pretty tough problem.
No, it's not. Your test is good. It's already been written.
What do you mean by it's good?
It's good.
Dr. P, how much you let me see it before you tell us?
No.
Yeah, I know. Give us a sneak peek.
You know, I am.
Early viewing.
Right here.
Okay.
Is it even, odd, or neither?
Even.
Oh my gosh, is it symmetric about the y-axis? If I fold that along the y, it's so neither, it's not even funny. I mean, but you could verify it algebraically. There is no, I see no symmetry. Neither even, not odd, nor odd, nor even, neither even nor odd.
Oh wait, is odd symmetric about the x-axis?
About the origin, y and x.
Uh,
What's the maximum number of turning points?
3.
3.
Yeah, how many do I have?
Either.
You've got 2, 1,
1.
How many should, I can either have,
1.
1. Only 1.
for degree 3, I can have 1 or 3. Mm-hmm.
So
And what is the y-intercept? 0, 0. Okay, good. All right, so that's fun with graphing. So there's a lot of stuff going on here. A lot of stuff going on here. You have a My Math Lab, so make sure that you stay on top of that. We're moving forward with the packet next week. There's a lot. Y'all did well. I'm impressed.
What does
You had